Hi everybody, welcome back. This is Unit C, Lesson 3, the development of the area of a triangle. The title of this investigation was Sailboat Racing. So if you recall, we looked at a race course for racing boats and worked from that contextual problem to develop the formula for the area of a triangle. If you will get your study guide packet, we're going to review some vocabulary, look at the height or the altitude of different triangles, acute, right, and obtuse. And then we're going to look at the development of the formula for the area of a triangle, where that came from, and work some practice problems. So get all of your supplies ready, and we'll be back in just a moment. Okay, we're going to start by looking at a triangle. And we're going to approach this with the assumption that we don't know what the formula for the area of a triangle is. So we started off by just looking at a triangle itself and seeing if we duplicated that triangle, could we create a shape that we have already worked with, such as a rectangle, a square, or a parallelogram. So what we did was we duplicated our triangle and put them side by side, and you notice when we do that, we end up with a parallelogram. So using that knowledge, we learned in Lesson 2 that the formula for the area of a parallelogram is base of the parallelogram times the height of the parallelogram. And since we're trying to find the area of the triangle, not the entire parallelogram, if we cut that value in half, that would give us exactly the area of a triangle. So that is where the formula for the triangle area comes from. It's by starting with a parallelogram and then knowing that it took two triangles to make that parallelogram. And you recall we can also write that as 1/2 base times height. But multiplying by a half or dividing by 2 are the same thing. Okay, so if we take a look at the first problem set in Lesson 3, the first asks us to draw the segment that represents the height of each triangle. So if you recall from our lesson in class, we talked about where the different heights could lie. The height or the altitude is the perpendicular distance from a base to the opposite vertex. So if you look at number 6, the base is labeled as B, and the perpendicular distance from that base to the opposite vertex would be as shown. Recall that a triangle could have 3 different bases depending on its orientation, and therefore it could have 3 different heights. But in this case, we're given the base that we need to use, and so this is the only height that is allowed. If we look at number 7, we talked about if we have a triangle that has an obtuse angle in it, then we know we are going to have a height that lies outside the triangle. So we extend the base so we know where to drop the perpendicular segment to, but in this case the base is this distance, 1, 2, 3, 4, 5 units, and the height would be 1, 2, 3, 4, 5, 6 units. So when you have an obtuse angle, you're going to have a height that drops down on the outside of the triangle. Let's go ahead and look at that third option that we have. When we have a right triangle, and in this case you notice that one leg of your triangle is missing, and that just happens to be because when you have a right triangle and the right angle is connected to the base, then the height is actually that side of the triangle itself. So the height is 1, 2, 3, 4, 5, 6 units on this triangle. So to recap, remember if we have a right triangle, the height could be a side of the triangle. If we have an obtuse triangle, the height lies outside the triangle and the base is just the original base. It's not the extension that we need. And then if you have just a plain old acute triangle, your height lies inside like you would expect it to. So if you'll pause the video here and take a few moments to go ahead and continue drawing the altitude or the heights of your triangle for the rest of this problem set, we'll be back in a moment. Okay, in this second problem set of lesson 3, we are asked to calculate the area of triangles. And as you recall from the beginning of the video and from the lesson that we did in class, the area of a triangle is found by base times height divided by 2. And like I said before, some people like to use 1/2 base times height. Either formula is acceptable. So on question 12, you can see that I have a base of 4 centimeters with a height of 3 centimeters. I can go ahead and simplify 4 over 2. So I have 2 times 3, or 6 square centimeters. So the answer to question 12 would be 6 square centimeters. I would like to look at question 15, simply because the base and the height are oriented in a slightly different configuration. So again, I'm going to use the formula base times height divided by 2. The base of this triangle is actually vertical in this case, and it is 20. I know this has to be the base because it forms the right angle with the height. So this must be the base side. And the height is 11 over 2. Go ahead and simplify my 20 over 2. I get 10 times 11, or an area of 110 square millimeters. 110 square millimeters. And then the last one I'm going to look at is 16, because it is an example of an obtuse triangle where our height lies outside. And again, our base is in a slightly different orientation. Our triangle was not sitting on the base. So here I have an area, again, of base times height over 2. My base in this case is 4.5 with a height of 4. Remember that the height is this distance, even though it's outside the triangle, but the base is only the original part of the triangle, not the extension. Okay? Then I still have divide by 2. I like to go ahead and simplify here. So I will have 4.5 times 2, or 9 meters squared in this case. So the answer to 16 is 9 square meters. So again, pause the video and finish the problems on this section of the study guide. As soon as you're finished, you can check your answers on the answer key on the website, and we'll be back with the next problem set in your study guide. Okay, welcome back. The next problem set on lesson 3 is to discuss what is similar or different about the areas of each triangle. And we're specifically going to be looking at the base and the height and the relationship between the area of the two triangles given those relationships. So one of the techniques I like to use is to highlight the two triangles I'm looking at, so it's easier for me to keep them straight in my head. So the first triangle is triangle ABC. So I'm going to go ahead and trace triangle ABC. in yellow. Then the next triangle I'm looking at is triangle ABD. So kind of on the outside of that, I'm going to trace ABD. So it's easier for me to visualize the two triangles that I'm talking about. So I'm going to start this off because base BC is half the length. Oh, I'm running out of room here. Hold on just a second. Okay, let's try that again. Because base BC is half the length of base BD, and both heights are equal, the area of the smaller triangle, triangle ABC, is half the area of triangle ABD. So if I just cut the base in half, but I keep the height the same, that causes the area of the smaller triangle to be half of the area of the larger triangle. So why don't you pause the video here and take a look at 19 on your own and see if you can determine the relationship between the two areas using the base and the height. And I will be back just a moment to do that one with you. Okay, number 19. I hope you tried it on your own, because it's the only way you're going to get any better is to try some for yourself. The first thing I'm going to do is highlight the triangles that I'm talking about so it's easier for me to visualize what's going on. So I have the smaller triangle FHG. So, oh no, that's the big one, isn't it? FHG. So I'm going to highlight triangle FH, oh that's J, FHJ in yellow, and then the smaller triangle of HKI in pink, so I can visualize what is going on here. And I can see that both of my triangles are right triangles. The smaller right triangle has a right angle on the right side, and the larger triangle has a right angle on the left side. So I'm going to start off again. Since base, now I'm going to write this base IH because I'm going to start at the right angle because these are congruent or similar triangles, so I need to write the points in a certain order. So since base IH is, you notice it's 3 units, and the base of the larger triangle is 6. So since base IH is half the length of base, and again I need to start at the same spot, so starting at the right angle, base HJ, and now I'm going to look at the heights. So the height of the smaller one is 3, and the height of the bigger triangle is 6 units. So, and the height, I'm going to start at the top of the triangle and come down. So the height KI is half the height of the height of FH, then the area of triangle KHI is 1/4 the area of FJH. Now again, you have to be very specific in what order you name the vertices or what order you name the endpoints of the segments when you're talking about similar triangles such as these, because they have to be matched up. Also, you might be wondering, how is it 1/4? Well, it's pretty easy to see now that we have it color-coded that the pink or purple triangle is 1/4 of the 4 equal triangles of the larger triangle, of the yellow one. But another way to think of that is we multiplied the length of the larger triangle by 1/2, and we multiplied the length of, or the height of the larger triangle by 1/2, and then when you multiply base times height, you end up with 1/4. So that's how you get the area being 1/4 that of the larger triangle. So that's probably the hardest one on this problem set. But if you will take a few moments and try the other problems, you can check the answers on the website under the resources page. The answers for the study guide are there. But if you still have trouble and don't understand the answer key, you could always see me in class or after school or during lunch, and I'll help you with this problem set. So good luck. Okay, the last problem set I'm going to look at for Unit C, Lesson 3, triangles, is the last problem set of the study guide, problems 26 through 30, where we have an unknown measure. And the reason I wanted to go over this was to help you set up your algebraic equation. Many of you can do this quickly in your head or with a calculator, but it's important at this point that you know how to set up the formula and use your algebraic steps to solve these problems. So since I have the area, I know I'm going to start with the formula for the area of a triangle. And like I said before, I prefer writing it in base times height over 2 form. It is up to you. Obviously, you know 1/2 base times height works just as well. Next, I'm going to substitute in the values of the measures I know. So I know that the area is 30 square meters, and I know that the base is 15. I do not know the height, that's the value I'm looking for, over 2, because the 2 is part of the formula. If I can at this point, I like to go ahead and simplify here if I have an even number on top. But 15 over 2 is going to give me 7.5, and it's just as easy to go ahead and undo this divide by 2 at this point. So I'm going to go ahead and do that. Multiply both sides by 2, which would give me a 15 times h on the right and 60 on the left-hand side. To get the h by itself, I know I need to divide both sides by 15. Anything over itself is 1. 1 times h leaves h. And I know that 60 divided by 15 is 4. So my height in this case, the height in problem 26 is 4 meters. Using my algebraic formula and steps to solve an equation leaves me the height of 4 meters. So let's go ahead and look at one more that is oriented in an awkward position. Let's look at number 30. So if we take just a moment and switch papers here, we can look at number 30. Here we have the base and the height. So we're just missing the area. This is a straightforward area problem, but since it's oriented in an awkward position, I wanted to make sure that we knew what was what. So in this case, since my perpendicular line has been dropped in that direction, I know that the height is 8 inches. That leaves me with a base of 5/3 inches. Okay, so my base is 5/3. I'm going to go ahead and start with the formula. Area is base times height over 2. And if you notice at this point, this is where having it written this form is probably not the best way. So I wanted to kind of point that out. If I put in my base of 5/3 and a height of 8 all over 2, some students start to get a little nervous at this point because we have a fraction within a fraction. But since this is all multiplication and division, this is really just one term, and I can go ahead and simplify right here at 8 over 2, or 8 divided by 2. So that would leave me 5/3 times 4, because 8 over 2 simplifies to 4. So you know that we have an invisible 1, which means we are left with 20 over 3, or 6, because 6 times 3 is 18, which would leave me 2 leftovers. So 6 2/3, or 20/3 inches in this case. So I just wanted to point that out because it was oriented in an awkward position, and it ended up with a fraction inside of a fraction if you use the formula base times height over 2. So just to make sure that there was no confusion on that, this is the end of section 3, triangles. So if you will go ahead and take a break, and when you're ready, come back and watch Unit C, Lesson 4. We'll talk about the development of the formula for the area of a trapezoid. See you soon.